So the title of my paper is Mondrian Conformal Predictive Distributions, and this is joint work with Ulf Johansson and Tuve Löfström. So I will start out by very briefly introducing conformal predictive systems and focus in particular on so-called split conformal predictive systems. And I will discuss some problems that can be solved using split conformal predictive systems, but also point out a problem that is more difficult to solve using a single split conformal predictive system. And to solve that particular problem, we propose Mondrian conformal predictive systems, which is actually a set of conformal predictive systems arranged in a Mondrian taxonomy or using a set of categories. I will show in what way this solves the addressed problem and then also present a more large-scale empirical investigation where we compare the Mondrian conformal predictive systems to the original split conformal predictive systems, but also when it comes to efficiency with regular conformal regressors. So, and I will mainly assume that you are familiar with conformal regressors because that will also help very much when it comes to the understanding of conformal predictive systems. So, and the focus here is on regression problems. So conformal predictive systems for regression, they output cumulative distribution functions or what's referred to here as conformal predictive distributions. So this means that we, for a single test instance, rather than getting a prediction interval out, as we do with a conformal regressor, or even a point prediction, which we get by a standard regressor, we here instead get a predictive distribution. So by this distribution, we can ask what is the probability that the true target is below a certain threshold. And clearly, such distributions can have many uses. And in fact, we can see that they can be used for, say, the original task of conformal regressors. We can get out prediction intervals, and we can even get out point predictions in various ways. So here we have an example where we have a certain test instance, and we have a conformal predictive distribution for this particular test instance. And we can see that the probability increases with increasing values for the y's. So by increasing the threshold, the cumulative probability increases. So a very natural point that we could be interested in is what we refer to as the median here of this distribution, where the probability of observing a lower value is 50%. That the true target is lower than this threshold, and the higher value is also 50%. So it's really in the middle of the distribution. And if we would like to extract a prediction interval with say 95% confidence, then we can also use the underlying conformal predictive distribution to first find the point where we have the 2.5 percentile, and then find the value for the 97.5 percentile, and use these endpoints to define the prediction interval. So there we will have an interval with 95% confidence. Okay, so this sounds very fine, and it can be used in many other ways as well, not only for getting point predictions and intervals, but we'll start having a look at how we can actually construct such conformal predictive distributions. And this is done by so-called conformal predictive systems, and we focus on one specific type of conformal predictive systems, namely split or inductive conformal predictive systems. And these are very much inspired by split or inductive conformal regressors. So the steps that we have to follow are very much the same, at least initially, compared to the conformal regressors. So again, what we do, we start by dividing the available training data into two disjoint subsets. So we have the proper training set and we have the calibration set. And then using the proper training set and some algorithm that we have at hand, we build an underlying model. So we may use any learning algorithm. And we focus on regression problems here, so it should be a regression algorithm. Then we go ahead and calculate scores for the calibration set. So alpha 1 to alpha q. So we assume we have q instances or examples in the calibration set. And as you can see, the scores we get here are very similar to what we normally calculate for conformal regressors. The only difference here is that we are actually using the residuals in the numerator and not the absolute value of the residuals. So that is, we take the actual value for the calibration minus the predicted value using the trained model. And then we have a difficulty estimate, sigma. So we may have a separate function that can help us estimate whether a certain instance is difficult to predict or not. Or we may decide to have a constant for the sigma. So now we are done with the first part, and now we can use the system to produce predictions for test instances. So for each test instance that we encounter now, we assume one test instance to be the x, and we should get a difficulty estimate using the same function that we had for the calibration instances. And then we calculate the following scores, namely we multiply in the sigma into all the alphas in the calibration set, and then add the prediction for the test instance. And then we just sort them in ascending order. And now we have all the information we need to form the predictive distribution for this particular test instance. And this is now simply done by using the calculated and ordered scores so that we see how large fraction for a specific y or threshold value that we're interested in, what is the fraction of scores that we have observed before that are less than this. And we use that number together with a small random value between 0 and 1, a uniformly sampled value for smoothing purposes, and then we get the probability. And then there's a special trick also to handle ties, but we don't need to focus on that now. So now we have a very straightforward procedure for producing conformal predictive systems. So now, once we have built the underlying model, we have calculated the original alphas for the calibration set, and now we may get some test instance. So for example, on the top left here, we have a prediction that for this particular test instance, the predicted value is 1.5, and we have a difficulty sigma of 0.1. And using the calibration, the scores for the calibration set, we obtain the predictive distribution. Okay, that's fine. And now if we encounter a new test instance, say with the same difficulty, but we have a differently predicted value. So we increase it slightly, the prediction. So what will happen with the output conformal predictive distribution is it's shifted along the x-axis. So the shape will be exactly the same, but we just shift it. But on the other hand, if we encounter a new test instance where we make the same prediction, but the difficulty increases, what happens is that the shape is now changed so that it's scaled out along the x-axis. So the curve will be more flat when we have a more difficult instance, and more reduced or shrinked when we have along the x-axis when we have a more easy instance. Okay, so this now allows us to produce different conformal predictive distributions for different test instances. So clearly, if we have a constant value for the difficulty, we will simply just move around the same distribution, but with different locations. Okay, so what can this now be used for? Well, one interesting observation is that if the underlying model is making some systematic errors. So maybe the model is frequently overestimating the true target. So this means that the residuals will, to a large extent, be negative. And if we, from such a set of observations, from the calibration set where we have observed the negative residuals, and then build for a certain prediction or construct the conformal predictive distribution, we can see that we may actually shift for the original prediction, which here is this orange vertical line, we can see that if we compare it to the median of the corresponding conformal predictive distribution, the median is clearly much lower than the original prediction. And this is very interesting because if we now, for example, would like from such a conformal predictive distribution, would like to output, say, a prediction interval with 95% confidence, and these are depicted here and here, the lower and upper bounds, then we can see that in fact, the prediction of the underlying model is not even within this prediction interval. So if we would ask the conformal predictive system to output a conformal predictive distribution for this particular instance, it may be that the prediction interval that we extract in the end does not include the underlying prediction or the prediction of the underlying model. And this is a fundamental difference to how we come up with intervals using the conformal regressors, because they're always centered in the middle of the prediction intervals. So this means that if we have a systematic error, we can actually, by replacing the original prediction with this median, for example, we may correct for this error. So we can correct for the bias of the underlying model. So this is very useful in some cases. But in other cases, we may have some difficulties. And in particular, if we observe this systematic error to vary, say, with the predictions that we make. And this is not very uncommon. So for example, we have a model where whenever it outputs a very small value, it's actually overestimating the true value. So it has difficulties pushing the predictions towards the lower end. And at the same time, it may have difficulties pushing the predictions towards the upper end. So for the high valued predictions, the residuals may be positive. So this means that if we would like to correct these in some way, then we cannot do this using a single conformal predictive system, because it can only push the predictions in one direction. So we have to choose whether correct for the lower errors or the upper errors, or if we would average over all the observations here, we would probably not push it anywhere. So how can we solve this problem? If we can't use a single conformal predictive system, what should we do? Well, our suggestion is actually to use multiple conformal predictive systems. And we propose to do this using a Mondrian approach. So we just reuse this famous idea of dividing our observations or instances into categories. So this means that we use the same division into categories both for the calibration instances and the test instances. So what we would do is that we somehow divide the calibration instances into subsets, and then we build a separate conformal predictive system for each category. And whenever we now have a new test instance, we will just see or assign it to one of the categories and use the corresponding conformal predictive system. So now an obvious question is, of course, how should we go ahead and form the categories? Well, depending on the purpose we have, we may form it in many different ways. But here, if we want to solve this specific problem that we saw, namely that we have these heteroscedastic residuals, then it's very natural to form the categories based on the predictions of the underlying model. And this is something we will have access to both for the calibration instances and the test instances. So what we can do, and this is even more straightforward, we can just say, okay, let's bin all the predictions into equal sized bins. So we may use the calibration instances or the predictions of the underlying model to find separate bins, non-overlapping bins, and then form one system, conformal predictive system for each bin. So if we do this, so let's have a look at one illustration here. So if we say using this one of the data sets that we actually will use later in the empirical investigation, and we take half of it to build an underlying model, a random forest in this case, and we use the other half as a calibration set. And then we don't use any normalization or anything, but just form we have 5 different categories. In this case, I will only show 3 here, where we have the 20% lowest prediction in the first one and the 20% highest predictions in the last category, and the 20% in the middle for the third category. And these are actually the 3 results from those 3 bins that I show here. And what we do with the calibration instances in each of the bins or categories is that we build a conformal predictive distribution for the mean prediction in each bin. So this is just an illustration. So we take the mean value in each of all the predictions in each bin, and then we can see how will the corresponding conformal predictive distribution look like. And here we can see that for the very first bin, where we have the lowest valued predictions, we can see that here is exactly the example I showed you earlier, namely that if we look at this mean prediction in the first bin and form, say, a prediction interval using the conformal predictive distribution, we can see that it will actually exclude the prediction. And if we would, instead of having the underlying model's prediction, but use the median of the conformal predictive distribution, it will actually push the prediction down. And this is exactly what we wanted, because we saw at the lower end, we had negative residuals. So the predictions were actually too high, so we want to push them down. In the middle bin, we don't see this, so there are less of a systematic error there. So not much correction will take place if we replace the original prediction with the median. But on the other end, where we have the highest valued prediction, and we take the mean prediction in that bin, we can see that they will actually be pushed upwards by taking the median instead. So this is very nice, but what happens now if we would apply this at scale? And so we decided to do an empirical investigation, and we, in some sense, replicated several of our previous investigations in that we will use the same number and quite large number of data sets, 33 data sets using cross-validation, etc. But what we are really after here are primarily to compare the Mondrian conformal predictive systems to the regular conformal predictive systems. And we compare both standard or non-normalized with normalized versions. And the non-normalized means that we simply have a constant difficulty estimate. And now when we evaluate conformal predictive systems, it's quite common to use the continuous ranked probability score, but unfortunately this cannot be used for evaluating conformal regressors. So when we consider the first performance metric, we will only compare the 4 variants of conformal predictive systems. But then we can also look at the efficiency. What happens if we extract prediction intervals from the distributions? And then we can compare it directly to the conformal regressors. But then, since I've been talking a lot also about correcting predictions using the medians, we will actually take a look what happens to the mean absolute error and mean squared error if we actually move the predictions according to the median. For the conformal regressors, that will not have any effect at all, since we always have the middle of the interval will be the underlying prediction of the underlying model. And in this particular experiment, we consider random forests, and since they use bagging for training, it means that we, in this case, can use out-of-bag predictions for calibration. This is something that we have done before, but obviously if we use some other type of underlying model, we should set aside a calibration set. But then we have to decide somehow how large this calibration set should be. And for the forest, we use their variance of the individual trees, their predictions or disagreement as a difficulty estimate. So if all trees or almost all of them are close in their predictions, we consider an instance to be easy, while if there is a large disagreement, it will be more difficult. So these are used, the same difficulty estimate is used for all normalized approaches. Okay, so now since we are getting results over 33 data sets, what we can do is actually average the ranks of the method. So if we start out with the continuous rank probability score and look at the average ranks of the conformal predictive systems, we can see that the Mondrian approaches come out with the top average ranks. And in fact, if we do a Friedman statistical test followed by a Nemeni post-hoc test, we can see that the observed differences in performance here are actually significant at the 95% level. So we can conclude here with some certainty that the Mondrian approaches, here all Mondrian approaches are using 5 bins, and this has not been tuned in any way. So they are outperforming using a single conformal predictive system, which seems to be very good. If we look at the efficiency or size of the intervals, and now we just more or less arbitrarily shows the 95% confidence levels, we can see that we don't have to pay a price for using the Mondrian approaches. So when we extract the intervals from Mondrian conformal predictive systems and conformal predictive systems, they are, when normalized, they are about the same as when we use conformal regressors that are normalized. The only significant difference here is that the non-normalized versions of conformal regressors and conformal predictive systems, they are clearly worse, while even the non-normalized Mondrian approach is still at least not very far behind the others. And there is not much difference if we look at either mean efficiency, size of the intervals, or the median efficiency. And now finally, we also look at the predictive performance or the point predictions, since we can use the conformal predictive distributions to correct by moving the predictions towards the, or replace the original prediction with the median of the distribution. And here, interestingly, we can see now that if we use the Mondrian conformal predictive systems, either the normalized or non-normalized version, we will actually improve by replacing the original prediction by the median of the distribution. But this is not the case when we use the original conformal predictive systems, because there we will have only one system built trying to cover errors at both ends, while in the Mondrian case, we will have more specific models tailored to certain, say, subsections. Interestingly, the use of Mondrian approaches improve when it comes to mean absolute error, but for mean squared error, using the median is not very effective. So here we can't see any longer significant improvement, say, compared to using the original prediction. Okay, so to summarize, what we have seen is a quite straightforward extension of conformal predictive systems, which we call Mondrian conformal predictive systems. So what we simply do is that we somehow decide to divide all the examples into categories. And then we build a separate conformal predictive system for each category. And if we base the categories on the predictions of the underlying model, then we have showed by the empirical investigation that we can significantly improve the continuous ranked probability score compared to using the original conformal predictive systems. And we do this without actually sacrificing efficiency if we want to extract intervals, and we can actually gain something from doing this by using the median of the distribution to correct the predictions of the underlying model. And now, of course, we have just scratched the surface here. So there are lots of things to look at. We can look at other ways of forming the categories. So we just used this binning, and one of the reviewers suggested using clustering techniques. And in fact, we investigated that early on without very much gain, but that could certainly be explored further. We can consider using other models than random forest, of course, and one interesting direction of future work is to look at other ways of extracting the intervals. We don't have to, even if we're interested in a 95% confidence interval, we can in fact change the upper and lower bounds. We could perhaps do that so that we gain some efficiency. And also the point predictions, maybe if we're interested in mean squared error, for example, then we should perhaps not go for the median of each distribution. Okay, thank you very much.